So we left off, we had done some trial and error to try to come up with a way to make a wheel that is moving, and we can model a fixed point on the wheel, calling it like a bike light or something like that. So that was what we did in that first part, and we ended up ultimately coming up with this modeling the point, and this modeling the wheel. And if you type both of these things into Desmos and have A from 0 to 100 and just hit play, you should have a wheel that's constantly moving down that x-axis. So it might have been kind of confusing about how we came up with all that, though. So I want to use a little bit better reasoning and actually connect this to vectors. So we're going to define a vector that starts at our starting point, and that vector is going to point to where the light is at any given time. So this is a kind of difficult task that is simplified by breaking it down. So we need to be able to define this vector, and not necessarily just that one. I mean, we need a vector that will define this at any point. So we need like that vector too. But we can just pick one to start with and just call it a general vector, and this will tell us how to define all the vectors. So we need to be able to have a vector that points from here to here, right? Well, so that would require that we have a horizontal component and a vertical component, right? Horizontal and vertical. So how can we come up with those? How can we determine this vector? It's not obvious. It's not obvious. So what we are going to do, though, is we're going to deal with the point of the circle that we know more about, the center of the circle. Because the center of the circle is only moving horizontally. It's not moving vertically. It's just going like this. Okay, because if it's in the center, the wheel rotating doesn't do anything to it. So we can have the vector that points at the center of the circle, and that's a little bit easier to deal with because it's easier to determine the horizontal and the vertical component of the circle, of the vector pointing at the center. And I'm going to show you how in a sec. But we don't want to be here, we want to be here. So we add these two vectors to get here. So how can we get here? Okay, we're just going to add one more vector coming from the center pointing at the bike light. So now we're going from here to here to here, which takes us here, right? We end up at the same point as if we were to just go like that. Okay, if we add vector 1, vector 2, vector 3, we still end up pointing at the bike light. So what we need to do is we need to define this vector, and this vector, and just add them all together, and that'll be the equivalent of having the red vector. Okay, so we need to determine this horizontal and vertical component, and then we need to determine this vector, what is that, and that will give us the vector that we're dealing with, that we're hoping to define. Okay, so those three are going to work together to give us the red vector. So first, it's going to be helpful to label some points. So we'll say this is point 0, okay, or we'll say O, okay, and this is point A. So this is vector OA, pointing from O to A, OA. Okay, vector AB is going to be from A to B, okay, point A to point B. And then vector BP is going to point to our bike light, which we're just going to call point P. Okay, and what we ultimately want to determine is vector OP, which is going to be the combination of OA, AB, and BP. Okay, this notation just means that we are a vector that starts at one point and goes to this point. Starts at one point and goes to this point. So we're going from O to A to B, and then B to P, which is going to ultimately be O to P. Okay. So I'm first going to argue that OA is just r theta comma 0. The comma 0 is the easier part because if you look at our vector OA, what is the vertical component of that? It's not going up vertically at all, so it has a vertical component of 0. So y then is r theta, our x component. Y is r theta, this length. So that's what we're saying, is that this length is r theta. So this is the length that is equivalent to this length. So I probably didn't do a very good job of doing this to scale, right? But the wheel has just moved, right? It's moved this way, and it's covered this amount of ground, which is the equivalent of how much ground the wheel has touched, right? Or how much of the ground has been touched by the wheel. And that is this amount of wheel because we've turned this angle theta. So y then is this distance r theta. So let's just pretend that theta is pi over 6. We know that the circumference of the entire circle is 2 pi r, right? So if we've only covered how much of the circle have we covered if we've only gone pi over 6? Okay, well, 2 pi. If we recognize that the whole circle is 2 pi, okay, how much does a pi over 6 chunk represent? 1, 2, 3, 1, 2, 3, right? 1, 2, 3, 1, 2, 3. Okay, very bad, but it's fine. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So we have basically split our circle into 12 little chunks if we divide it by pi over 6, right? So we're taking our circumference, and we are dividing it by 12 because this is 1/12 of our circumference because pi over 6 represents 1/12 of the overall circle. So we take our 2 pi r, our circumference, and divide it by 12, and that gives us pi over 6 times r, which is just r times theta, right? R times theta. If we make theta pi over 4, I'll probably do better at drawing this one. Okay, if we split our circle up into, if we split pi of our circle up into fourths, okay, then that splits the whole circle up into eighths, right? Each slice is 1/8 of the circle. 1, 2, 3, 4, 5, 6, 7, 8. So if we make theta pi over 4, that means that we have traveled on 1/8 of the circumference of the circle. So we can take our circumference 2 pi r and divide it by 8, and that gives us pi over 4 times r, which means this distance would be pi over 4 times r times theta, pi over 4r. Okay, so in general, this is always just going to be whatever r theta is, right? If we do one full rotation, that means that the ground has been touched by every single piece of the circumference, which means it's going to be 2 pi times r, right? One full rotation. So this is just r theta, vertical component 0. This one's going to be easier to determine because it's going straight up, meaning its horizontal component is 0. And then what's its vertical component? How far up does it go? Well, that's just the radius of the circle, right? Just the radius of the circle, because it's pointing from the edge of the circle to the middle. And so that is representing one radius. So that one's easier to figure out. Now, vector BP is going to be tougher, so I put it over here so we could look at it a little closer, right? We're calling this theta, meaning this is the angle that the wheel has rotated. Okay, we know this is the radius because it's pointing from the center of the circle to the edge of the circle. So what are the horizontal and vertical components? Why don't you stop and think, how can we use right triangle trigonometry here, right triangle trigonometry, to determine how to define those horizontal and vertical components? So what if I say sine of theta, and let's call this x and y for now. What if I say sine of theta equals, well, what's opposite? It's x. What's the hypotenuse? It's r. So then x is just r sine theta. Okay, what if I do cosine theta? Okay, well, what's adjacent to theta? Y. What's the hypotenuse? R. So I get cosine theta is y over r. So y equals r cosine theta. Okay, so that would mean that we can just write BP like this. Yeah. Oh yeah, so I should specify. Technically, it's going to be a negative r, okay, because the horizontal component is pointing this way, the vertical component is pointing down, so both of these are going to be negative vectors, okay? So it's actually going to be negative r sine and negative r cosine, but the other reasoning still stands, okay? But because it's pointing down and left, okay, negative, negative. So that means we can write BP like this. Here's our x, here's our y, here's our horizontal, here's our vertical. Negative r sine theta, negative r cosine theta. So now we need to do OA plus AB plus BP to get OP. So we have r theta, comma 0. We have 0, comma r. We have negative r sine theta, negative r cosine theta. And if we want to add these, we just need to add their components. So what is r theta plus 0 plus negative r sine theta? That is going to give us r theta minus r sine theta. We just add all three of these components. Okay. What is 0 plus r plus negative r cosine theta? That's just going to be r minus r cosine theta. And I'll have that neater on the next slide. So here it is. We have r theta minus r sine theta, r minus r cosine theta. So what we should notice is the horizontal component continually gets larger as this wheel goes because this piece is getting bigger, right? Bigger as theta grows, okay? Because we're going to multiply r by however much the angle has rotated, right, or however much time has gone on, either way. And that's just going to make this get bigger, which is going to make our x value continually get bigger, causing our wheel to move this way. But this one is oscillating in size because r is never changing. R is just the radius of the circle. Okay, r cosine theta is oscillating. So why does it make sense that y is oscillating and x is getting bigger? Because if you think of the vertical position of the point, it's just going up and down as it travels around the circle. It's never going to go higher than that or lower than that because it's attached to the circle. So it only goes up and down, it oscillates. While the x value has to get bigger because the wheel is moving this way. So this is getting bigger while this oscillates. So now in Desmos, we're going to use time. So we will say, and also what we're going to say is that the radius of our circle, we're just going to let it be 1. Okay, so we'll let r equal 1. So then we have 1 times t minus 1 times sine t, and then we have 1 minus cosine t. So graphing this will give you the path of the bike wheel. It'll actually show you the traced path. So you can type that in. Okay, so, and then what we can do is we can go back to what we did before and have our point in our wheel that moves. And if you type all of this in, then, again, we have a little extra component here because we're going to let A be the radius of the circle. So that's going to allow us to change how big our bike wheel is. But in our problem, we just let r equal 1. So you can just set A equal to 1 for our problem. And then if you want to see what happens when you change this, you can mess with that. We're going to let B represent time. So this is passing time. And then so here's our bike light. Here's the path. Here's the purple point that actually represents the bike light. Here's the wheel. This is the wheel that is actually rotating along the axis. And then here's the path that we just came up with by messing with vectors. And we call this trace path a cycloid. That is the name of this curve. So we just figured out how to parametrically graph a cycloid by going through a bunch of vector components to come up with a vector that's always going to point at the path of the bike light. So again, to connect to our example, we had x is t minus sine t and 1 minus cosine t because in our example the radius is 1. So it's t minus sine t, 1 minus cosine t. If we replace a with 1. But if you want to make the radius bigger, then you should you'll have to multiply your time by whatever your radius is. So that's why we have this a out in front. And then b is representing time just so it can be a slider that's changing. So that's why b is replacing t here. So in our example here, b equals our changing time. So then this is going to be a key for a problem set problem because it's going to ask you to just write out the sliders for if you have a bike wheel with radius 5. So you can always just come back to this slide and see how you need to adjust your numbers. This was a complicated lesson. So if you use the Google Doc to submit questions, I can try to clarify stuff. And I'll also post another resource that you can use. So.